Okay. All right, thanks everyone for coming to my DDS. I'll just get right into it here. So some of the work that I've been doing, it all falls under this compass of data-driven modeling for robust Egomotion estimation. So let's get right into it and first introduce what Egomotion estimation actually is. So Egomotion estimation is the process of determining the motion of a rigid body using measurements from sensors attached to the body. So if we look at this system as a black box, essentially the quantities that we're looking at are this input is sensor data and an output that is a sequence of the relative pose measurements consisting of position and orientation quantities that represent how a vehicle or a body has moved over time. So these measurements can be compounded over time to produce trajectories that represent essentially how a mobile agent has traveled. So why are we interested in Egomotion? For our purposes, Egomotion estimation is an important component of robotic systems and more specifically autonomous robotic systems. So here, robots must first perceive their environment using sensors and localize themselves within this environment. And these tasks must be accomplished before downstream tasks like planning and control or actuation of the robot can happen. And so this perception, localization, and planning control paradigm is common among a lot of robotic systems. And my research is focused on the localization aspect of these systems. So in the domain of localization, there's a lot of ongoing research that typically involves developing methods that are more accurate, more robust, or more computationally efficient so that these systems can be deployed in real time. My research focus involves making localization systems, and in particular, Egomotion estimation systems, more reliable or robust to failure so that they can be used in increasingly more complex environments and across longer operating periods. And this is important to promote the long-term autonomy of mobile robots. And so one other thing to note here is another challenge for mobile autonomy is that these systems are required to operate alongside humans. So not only do these systems have to understand where in the environment they have to understand where all of the other mobile agents are, including humans. So my focus investigates methods that allow for localization of humans and robots within a shared space. So what type of sensors are used for localization? The most straightforward sensor is one that you all have on your phones, and that is GPS. So GPS provides direct position updates within a global navigation frame and is really useful for human navigation in many forms. But the main downside is that it requires an external signal from satellites to operate. So this signal is obstructed, for example, when operating within buildings or in urban areas. For example, the position estimates will be highly unreliable. So instead, mobile systems often rely on body-mounted sensors since they're more reliable and self-contained, and they don't rely on any external infrastructure to operate. So in my work, I'm focused on Egomotion sensors, which consist of inertial measurement units, cameras, LiDAR sensors, among others. And I focus on using IMUs and cameras for Egomotion estimation, as these sensors are low cost, compact, lightweight, and they're capable of producing 3D pose estimates. So let's briefly cover the basic operating principles behind inertial and visual Egomotion estimation. In the case of inertial Egomotion estimation, known as inertial navigation, position orientation estimates are both produced by integrating the signals from the gyroscope and accelerometer measurements on the IMU. And I won't go into a lot of detail about this process, but this diagram here shows the high-level components of an inertial navigation system. So first, the gyroscope signal, consisting of angular velocity measurements with units of degrees per second, is integrated to determine how the IMU orientation has changed over time. By compounding these changes in orientation, the absolute orientation of the IMU can be tracked. And so accelerometers, on the other hand, produce acceleration measurements in units of meters per second squared. And so after rotating these measurements to a global navigation frame and accounting for the effect of gravity, these measurements can be integrated once to produce a velocity estimate, and then a second time to produce position estimates. And switching over to visual egomotion estimation, this involves the detection and tracking of environmental features within a sequence of camera images. So by observing the same points in many frames, the 3D positions of these points can be determined through triangulation. And by observing how these points move throughout the sequence of images, the motion of the camera can be deduced. And this is typically done with what's called bundle adjustment. And lastly, it's important to note that many algorithms exist that combine measurements from both sensors. So this essentially produces an even more accurate egomotion estimate. And we'll talk about this more later on. So although egomotion estimation based on inertial and visual sensing has a rich history, the accuracy and reliability of existing systems can still be quite limited when these systems operate under challenging operating conditions. And these limitations are essentially due to the fact that, in general, most of these models are based on handcrafted or hand-designed components. And these, in turn, rely on simplifying assumptions to make the estimation problem more tractable. So let's use VO as an example. VO systems generally consist of a front end and a back end. And the front end is composed of a feature detector and tracker, which identifies stable key points or features within the images, and then establishes correspondences between frames. And the back end uses the feature correspondences to jointly estimate the 3 positions of these key points along with the camera motion. And for the back end to operate successfully, it's assumed that the front end is able to detect and match a sufficient amount of features that correspond to stable points in the scene. So within challenging operating conditions, for example, with severe lighting changes, many dynamic objects, or rapid vehicle motion, among others, front ends can fail to produce enough accurate feature correspondences, which can then cause the system to fail. So given these limitations, there's been a paradigm shift away from using traditional handcrafted estimators and towards using data-driven models instead. So these data-driven models, which can consist of modern machine learning components like feed-forward neural networks, convolutional neural networks, or recurrent neural networks, can be trained to learn this complex mapping between sensor data and egomotion. And unlike traditional estimators, these models are no longer dependent on some of the simplifying assumptions that have made traditional estimators more brittle and prone to failure. So as a result, these data-driven models, they have potential to be more robust than their traditional counterparts. And being data-driven, these models are able to learn directly from data and can leverage the vast amount of tools that have been developed in the domain of machine learning. So for example, by providing challenging training data to the network at training time, along with their ground truth egomotion labels, these models can be trained to operate robustly in degraded environments. So an open research question remains, to what extent should data-driven modeling be used over traditional modeling? This slide roughly summarizes the characteristics of each paradigm. So on the left, we have a classical model, which being built with handcrafted components requires a significant amount of domain knowledge to map the sensor data to egomotion. And in doing so, a number of modeling assumptions are therefore built in, which can limit the overall flexibility or robustness of the model. And this causes it to be brittle or prone to failure. And the one benefit of classical models is that when these modeling assumptions do hold, the accuracy is in general very high. And the other benefit is that by relying on handcrafted components, the interpretability of these systems remains high. So on the other hand, end-to-end trained models require no handcrafted components, and therefore they require a lower amount of domain knowledge to build. And for this reason, they're based on fewer modeling assumptions, and as a result, their overall flexibility and robustness is quite high. And in terms of the downsides, currently the accuracy of end-to-end systems, although it's been steadily increasing, still lags behind that of classical models. And this is also true with the interpretability of these models. And finally, there's a third class of hybrid models that combine classical and learned components in a principled manner to leverage the benefits of both paradigms. So the goal here is essentially to replace error-prone components of classical systems with more robust models while preserving the useful classical components that generally improve the accuracy and interpretability. And so in doing so, we're able to sort of leverage the benefits of both paradigms and mitigate the negative aspects of each. So how does my own research fit into all of this? My research investigates how data-driven models can be incorporated within Egomotion estimation pipelines to improve their overall performance. So my overall approach is as follows. First, I identify key failure modes within components of classical Egomotion estimators that can limit their overall performance. And then I propose data-driven solutions to either augment or replace these classical components. And finally, I demonstrate how these data-driven models can improve the overall robustness and or the accuracy of these estimators. And in particular, my thesis investigates how data-driven models can be applied to 3 different applications of Egomotion estimation. And so the rest of this talk will be divided into these 3 sections. So the first is on foot-mounted inertial navigation for human localization. The second is on visual odometry. And the third is on visual inertial odometry, where we use sensor fusion to estimate Egomotion from a combination of visual and inertial measurements. And the second 2 applications are focused on localization for wheeled and aerial vehicles. So let's start with our work in the domain of human localization. And in this application, our goal is essentially to produce high accuracy localization estimates in areas where GPS is unavailable. And for this application, using an IMU for inertial navigation is ideal as it's lightweight, low cost, and non-intrusive. So our system uses a foot or shoe mounted IMU and is based on the INS integration method that I introduced earlier. So here, given IMU measurements, the signals can be integrated to produce these relative orientation and position changes, which can be compounded together to produce a 3D trajectory over time. And we'll discuss why we actually mount the IMU on the foot next. So the current challenge with inertial navigation is that IMU measurements, especially those produced from low-cost sensors, contain a random noise term that produces errors within the state estimate when these values are integrated. And this leads to an unbounded error growth that occurs over time. So in this process, since we have 3 different integration steps, this means that the error within the position estimates grows cubically over time. And this can actually lead to catastrophic error growth within a matter of seconds or minutes. And so a unique solution to this problem involves mounting the IMU on the foot and applying what's known as zero velocity measurements when the foot is stationary on the ground. So since this occurs quite regularly during human locomotion, these measurements can be applied frequently to bound the overall error growth over time. And this solution is known as zero velocity aided navigation. And it's a popular solution for human localization. Typically, these systems are as follows. So instead of relying solely on this integration-based motion model, we now have these zero velocity measurements that are produced from a zero velocity detector, and they're fused with the integration-based motion model through an extended Kalman filter to produce essentially a refined pose estimate. And one of the key components with this system that we'll talk more about is the zero velocity detector, which takes as input a sequence of IMU measurements and produces a binary output that indicates which measurements correspond to a stationary IMU versus a moving IMU. And we'll talk more about this next. So we finally arrived at the first component of a classical system that's error prone and potentially requires an addition of some data-driven model. And this component is the zero velocity detector. So a classical detector is based on a likelihood ratio test that models the likelihood of the IMU being stationary. So given a current window of measurements, it produces this likelihood. And given 2 hypotheses, one being the null hypothesis that the IMU is moving, and the other being the stationary hypothesis, the LRT is the ratio of these 2 likelihoods. So when the likelihood of the stationary hypothesis is high and the likelihood of the null hypothesis is low, this LRT exceeds this hand-tuned threshold, gamma, causing the detector to produce a zero velocity measurement. One example of such an LRT is the angular rate detector, which produces zero velocity detections when the angular velocity norm of the gyroscope measurements is approximately zero, or in this case, whether it falls below this threshold gamma. And looking at a plot of the angular velocity norm shown on the right, we can see that this threshold-based detection can essentially be a good way to detect these zero velocity events. The challenge, though, with this threshold-based detection approach is that angular velocity readings are highly dependent on motion type. So if we expand this figure to show the angular velocity norm for different motions, in this case, stair climbing, walking, and running, the measurement profile for each is very different. So this means that the threshold that we've optimized for stair climbing motions is no longer valid if the user is walking or running. And so essentially zero velocity detections would no longer occur. So if we were to increase this threshold to accommodate all the motions, including running, we can see now that false positive detections will actually occur when the user is walking or stair climbing. So essentially the main takeaway here is, that there isn't any, there is no constant zero velocity threshold that's suitable for all motions. So for my first thesis contribution, I proposed two systems that use data-driven models for robust zero velocity detection. So here we preserve the same estimation framework that involves the use of the Kalman filter, but we propose two new data-driven zero velocity detection frameworks. So in the first system, we introduce a motion adaptive zero velocity detector. And at its core, this is still a detector that's based on the same likelihood ratio test that we introduced, but now we include a motion classifier, which takes as input a sequence of data and predicts the motion class of the user. For example, whether the user is walking or running. And then given the predicted motion, an appropriate threshold can be optimized for that particular motion type and used within the same classical detector. So this adaptive threshold method essentially allows for an approximately optimal threshold to be applied at all times, despite a changing motion type of the user. And in our second proposed system, we entirely remove the classical zero velocity detector and we replace it with a data-driven alternative. So we use an end-to-end trained recurrent neural network called an LSTM to produce these binary zero velocity classifications given IMU measurements as input. So we used, for our motion classifier, we used a support vector machine as the type of data-driven model that we used. So without going into a lot of detail, an SVM is a simple linear classifier that uses what's known as the kernel trick to transform inputs into a new feature space that is actually linearly separable. So our system takes as input a whole second of IMU data and then outputs a single motion class prediction that corresponds to that input. And this SVM is trained using a collection of training data that we acquired using IMU measurements. And then we also have to acquire the ground truth motion labels associated with those inputs. And for our zero velocity classifier, we use an LSTM network, which is a form of recurrent neural network. So LSTMs are one of the state-of-the-art models for sequential learning tasks. And the reason they're so effective is because they can take a full sequence of inputs and propagate a memory state through time, which allows the current prediction to be influenced by the full sequence of prior inputs. And the LSTM is trained using a data set of IMU measurements along with their ground truth zero velocity labels that we acquired. And we use a standard cross entropy classification loss to train this network. So to train these models, we had to generate our own training data. And we did this within the Vicon room at UTIUS, which has a motion tracking system that was really useful for providing the ground truth position of the IMU associated with each measurement. And so to generate training labels for a motion classifier, we simply had to hand label the data with the known motion class of the user for each trial. And to generate zero velocity labels, we essentially developed a novel data labeling procedure that labeled the zero velocity ground truth. And we did this using the Vicon system. And so after training these models, we incorporated them within our zero velocity aided INS, and then we evaluated the real-time position estimates that we produced from our system on 2 different data sets. So we collected one here at UTIUS, and we collected one downtown at Bayon Center. And so for the UTIUS data set, we had to survey ground truth positions on a number of floor markers placed throughout the hallways here at UTIUS. And we had a number of users perform mixed motion trials consisting of walking and running motions down the hallways. And we used these trials to essentially evaluate our data-driven zero velocity detectors alongside 2 of the other existing classical detectors. So in these hallway trials, we found that our data-driven detectors, being substantially more robust to varying motion compared to the classical fixed velocity or fixed threshold detectors, resulted in improved localization accuracy across this data. So here we show a top-down view for a walking trial and for a running trial. And our 2 systems, shown in orange and yellow, they closely align with the ground truth surveyed marker locations, which are shown in red. And conversely, the trajectories from the systems that use the classical detectors, which are shown in green and blue, both are substantially less accurate in these instances. And this is a result of the non-optimal threshold selection. So in the case of the walking trial, the threshold was set too high, causing false positive zero velocity events to occur. And this resulted in the trajectory length essentially being underestimated. And then the opposite happened for the running trial, where we can see there's this high drift region, which occurred because the threshold was essentially too low to detect these zero velocity events during running. And this caused this unbounded error growth over time. So summarizing the results from these hallway trials, we can see that our 2 methods had a lower average error throughout. And notably, we were able to prevent these failure cases where localization error catastrophically increased as a result of this improperly selected threshold. And one notable aspect of these results is that they also demonstrate the generalization capability of our learned components. Because in our case, for the LSTM classifier that we used, we actually only acquired data from a single test subject and trained the classifier with this data. And so the results actually from this, this data set are across 6 different users. So this essentially demonstrates that our classifier was able to generalize 1 to different gait patterns, to different people, and to different shoe types. And so we attribute this to our data augmentation scheme that we used during training, which I can discuss after the talk if anyone is curious. So in our next set of experiments, we evaluated our data-driven systems on trials involving stair climbing in a stairwell at Bayon Center on St. George campus. And for this experiment, our metric was the vertical position error when the user arrived at each new floor. So overall, we found that our data-driven detectors substantially improved the accuracy throughout these trials. So here we show one stair climbing trial where we plot the vertical height estimate over time. And the red lines here indicate the height of each floor, and the marker labels represent when the user arrived at each floor. So here we can see that our methods, again in yellow and orange, were able to accurately track the vertical height at each floor level, both through the ascent and the descent. And if we look at the blue and green plots again, corresponding to classical detectors, we can see by the end there's a significant amount of error drift that has accumulated. And the plot on the right summarizes the results of our stair climbing trials. So in this case, we see the LSTM-based classifier that we implemented achieved the best performance, even over our other approach based on motion adaptive thresholding. And again, this is sort of an interesting result because for training, since we only acquired data in the Vicon room, we didn't actually train this on stair climbing at all. So it was able to essentially generalize to this new motion. And lastly, this is just a system or a video of our system working in real time. So we implemented this real-time localization system using robot operating system. So this project, it resulted in 3 different publications, which include 2 conference publications and 1 to the journal, the IEEE Sensors Journal. And thanks a lot to Valentin Peretrukin for all of his contributions with this work. So next we shift our focus away from human localization and onto visual odometry, which is a form of Egomotion estimation that's commonly employed on autonomous robots. So here I'll present my contributions in this domain, which essentially involved, again, the use of data-driven learning to design robust estimators. So as I discussed early in the intro, classical VO systems that consist of this front end and back end, essentially with these systems, the most common failure mode occurs when the front end fails to detect and track a number of feature correspondences between frames. So to produce a more accurate and robust VO estimator that can operate in these challenging environments, there's essentially motivation to investigate correspondence-free methods that don't explicitly require features to be tracked or matched between frames. And one solution is to use data-driven learning to remove or replace these components entirely. So a strategy that's become popular recently is to replace the full VO estimator with convolutional neural network and train the system to learn this complex mapping from raw pixels to camera Egomotion. So in my work, we follow a similar approach. And in particular, we investigate this existing system. It's called the Learned SFM system, or Learned Structure from Motion system, which is an approach for jointly modeling camera motion and scene depth. So more on this next. The Learned system, or the Learned SFM system, is an approach for learning scene structure and camera motion in a self-supervised manner by minimizing a loss based on view synthesis. To do so, it employs a depth network, which when given an input image, produces a dense per pixel prediction of scene depth. And then it also requires this Egomotion network, which when given a pair of images, produces an Egomotion prediction between 2 frames. So the most notable aspect of this system, which I will discuss in more detail, is that it can be trained in a self-supervised manner, meaning no depth or pose labels are required at all. And we can do this by minimizing this loss that's based on view synthesis. So we'll show this next. So again, here's an overview of this baseline learned SFM system. And like I previously mentioned, we employ these 2 separate networks. So we have our dense depth predictions that are produced from the depth network. And we have our Egomotion predictions, which are produced from an Egomotion network that takes as input a target frame and a nearby source frame. And so using these quantities and the known camera intrinsics, we can reconstruct the target image from pixel values from the source image using a differentiable view synthesis module. And after this target image has been reconstructed from the source view, our reconstruction loss is then the per pixel difference between this image and the observed target image. So through gradient descent, at training time, the loss is minimized by backpropagating gradients from the loss through the view synthesis module and into the neural networks to update their weights. And throughout training, as the accuracy of the depth and Egomotion predictions improves, we can more accurately reconstruct this target image from the nearby source view. And so this is essentially the main source of supervision that we have to jointly train our networks. And my research in this area focuses on improving this system, which has some interesting properties. In particular, the ability to produce dense depth predictions alongside the Egomotion predictions is useful for a number of reasons, and we'll elaborate on those reasons shortly. But the second advantage is that it's self-supervised in nature. Like I said, it means we don't actually require any ground truth labels to train. So instead, the full system can be trained using a stream of raw images alone. And as a result, the collection of training data is substantially simplified, and it allows us to increase the amount of data that we use while saving time and money. So it's a more scalable approach than supervised learning. And lastly, the one interesting thing about self-supervision is that it facilitates lifelong learning, as the system can be continually retrained as new data is acquired. So this helps improve generalization when operating in new environments. And the learned SFM system, it's become very popular over the last couple of years, and many advancements have been made in a lot of different areas. My research focus has been investigating how monocular scale ambiguity can be addressed within this system. So like any other monocular system, scale ambiguity occurs as a result of the fact that images are 2D representations of a 3D world. So as we can see from this image, the projection from 3D to 2D causes many different size objects at many different distances away from the camera, all to lie within the same area on the image plane. So this monocular scale ambiguity poses three different challenges for our learned SFM framework. First, since the photometric reconstruction loss is not impacted at all by the scale of the predictions, the scale factor essentially will converge to some random off-unity value. And so to produce metric predictions, this scale factor would have to be determined using some form of metric information. For example, like using a known object size that's viewed within the scene and correcting for that at test time. In addition to the scale factor offset, the network predictions also suffer from interframe scale consistency. And so this means that there's some amount of scale drift that occurs over time. And the problem with this is that we now are no longer able to apply a constant scale factor that can correct for this. And then lastly, since this scale drift can be different between the depth and the Egomotion networks, and this is a result of the networks effectively being decoupled from each other, we also experience this inter-network scale inconsistency. So in the learned SFM system, these three factors can all be detrimental to the accuracy of the system. So we propose two separate modifications to the baseline learned SFM system in order to address some of the challenges that monocular scale ambiguity poses. So in our first contribution, we employ a scale recovery module to enforce metrically scaled depth and Egomotion predictions. And in our second contribution, we investigate how a more principled coupling between the two networks, the depth and the Egomotion network, can result in a more mutually consistent notion of scale that's shared between the two networks. So let's talk about these two sort of projects that we've worked on. For our scale recovery module, we minimize an auxiliary loss term alongside the standard reconstruction loss to encourage predictions from our networks to essentially become metrically scaled. And our scale recovery loss that we use utilizes a priori known knowledge about the camera height of that is mounted on a vehicle. So we assume this camera height to be constant over time, which means this loss is applicable generally for wheeled systems. So essentially, our scale recovery loss compares the known or the ground truth camera height with an estimated camera height that we produce from our system. And to estimate this camera height, we first have to isolate the ground plane using a ground plane segmentation network. And then we use a plane fitting procedure to estimate one, the normal direction of the plane, and two, the plane offset, which in this case is equal to the camera height. So essentially with this scale recovery system, by minimizing this camera height loss, we're able to constrain the depth and the Egomotion networks to produce metrically scaled predictions. So to implement this scale recovery loss, first we need some means of extracting the ground plane pixels so that we can use them to estimate the parameters of the ground plane. So that is the normal direction and the camera offset. And to do so, we develop a novel plane segmentation network that outputs a per pixel prediction indicating the confidence of that pixel belonging to the ground plane. And in the figures on the right, we can see some example predictions from our network. And we train this system or this network using a novel self-supervised procedure that we developed, which I can elaborate on later on if anyone is interested. So we incorporate our scale recovery loss at training time, and then we minimize it alongside the standard photometric reconstruction loss to produce our metrically scaled predictions. And so the figure on the right demonstrates the impact of this approach during training. So we can see that during the first epoch, the scale factor of our predictions is able to quickly converge to unity, and then it remains there for the rest of the training. And this experiment was performed on the Kitty dataset, which is it's an urban driving dataset. So in this second plot here, we show the impact of our scale recovery loss at test time on the same Kitty dataset. Here we can see that not only does the scale factor converge to unity, but it also has become more consistent throughout the sequence compared to a similar baseline system shown in orange that did not use any scale recovery during training. So basically this plot demonstrates that not only can we recover metric scale with our scale recovery module, but we're also able to reduce the amount of scale drift that occurs over time. And next, we'll move on to our second contribution to the learned SFM system. And this contribution addresses the fact that there isn't any proper coupling between the depth and the Egomotion networks. And the challenge with this is that it can limit convergence during training, as no explicit information sharing can happen between the two networks. And like I mentioned earlier, this is one of the reasons why inter-network scale and consistency exists between these two networks. So we address this limitation by investigating how the depth and the Egomotion network structures can be properly coupled to facilitate information sharing. And we do this both at training and at test time. So we develop what we call a tightly coupled network structure that employs two different coupling strategies. First, a feedback coupling, and second, an indirect coupling strategy. And I'll talk about each of these strategies next. So the first form of coupling that we employ is called feedback coupling. And this is applied to our Egomotion network, and it's illustrated in this figure. So here, rather than producing the Egomotion prediction via a single forward pass through the network, what we do is we produce multiple forward passes, and our network is then able to iteratively update the initial prediction within these additional forward passes. So in these subsequent passes, the source image that we provide as input to the network is replaced by the current reconstructed image. And in doing so, this network is now able to produce a pose correction, seen as delta t, that further aligns this reconstructed image with the target image. And this process is repeated for a specified number of iterations until the reconstructed image is optimally aligned with the target image. And the other notable thing about this approach is that by employing this feedback, not only does the network become a function of the current Egomotion prediction, but it also becomes a function of the current depth prediction. And so this coupling is what allows us to share information between the two networks, both at training and at test time. And here we visualize again this feedback coupling approach in a little bit more detail. So in the first pass, which uses the source and target image as input, the initial pose, T0 is produced. Then in subsequent passes, the source image is replaced with this reconstructed image, and a series of corrections shown as delta t are produced. And then with each correction, the reconstructed image becomes increasingly more aligned with the target image. And after the final iteration, we produce our final prediction by compounding together the initial prediction along with these corrections. And on the right, we visualize the impact of this iterative feedback scheme by showing the reconstruction loss as a function of the yaw angle prediction. So as our predictions are refined by performing multiple forward passes through the network, we're able to converge this initial prediction to the point at the minimum of this loss where the reconstruction loss is essentially the lowest. And the second form of coupling that we employ is called indirect coupling. And this form of coupling uses a test time optimization scheme to further reduce the self-supervised reconstruction loss on individual samples at test time. And we call this indirect coupling because the depth and Egomotion networks are implicitly linked via the gradient flow from the loss function during the optimization. So our test time optimization scheme refines the weights within the depth network, which causes the depth predictions to change in such a way that further reduces the reconstruction loss overall. So in this figure below here, we can see that after 20 optimization steps, the overall depth accuracy improves, and as a result, the per pixel reconstruction loss is reduced. So overall, we found that by coupling our networks together, the accuracy of the depth and Egomotion predictions substantially improved. And the left figure illustrates improvement on a test sequence of the KITTI dataset to sort of show our overall results here. As we can see, the trajectory produced from a baseline system, which is shown in blue, drifts significantly over time, but by introducing feedback coupling through iteration and then introducing indirect coupling through optimization, the accuracy is able to substantially improve. Notably, when comparing our method with other similar learning-based methods, we achieved state-of-the-art accuracy on some of the standard evaluation benchmarks on the KITTI dataset. So along with this improvement in Egomotion accuracy, we also were able to experience an improvement in depth prediction accuracy as well by employing these coupling schemes. So here's just some visualizations on the KITTI dataset and also on the ScanNet dataset, which is an indoor dataset. So final results here, along with improved performance on test data, we found that our coupling scheme also improved the generalization on new data. And one way we evaluated this is through a frame skipping experiment. So here we removed a number of images from a sequence to simulate high velocity camera motion. And we only include this, this high velocity motion at test time, so we don't actually include this at all during training. And in the plot on the right, we can see some of the results from this experiment. So we show that as more frames are skipped within the sequence, for the baseline one iteration model in blue, we see this accumulation of error. But as we apply more iterations, we're actually able to maintain the accuracy of our system. And then lastly, we conducted one experiment to show that our system actually is able to pass scale information between the two networks. So to do this, we modified the scale factor of all of the depth predictions within the test sequence. And then we used these new least scale predictions within our feedback coupling scheme to iteratively produce new Egomotion predictions. And notably, we can see that as more iterations are applied, the scale of the translation norm essentially becomes more directly proportional to the scale of the depth predictions. And this indicates that our coupling scheme really was able to facilitate the sharing of a mutually consistent scale factor. And so work in this area resulted again in 3 different publications. So we had 2 conference papers and 1 publication in the robotics and automation letters. And thanks again to Valentin for his contributions on these projects as well. So in the last phase of this presentation, I'll discuss my final contribution, which again is applying data-driven modeling to produce a robust VIO system. So having just developed this robust data-driven VO system based on the learned SFM framework, a natural extension of this work is to investigate how we can incorporate inertial data or inertial measurements into this system and perform sensor fusion to potentially achieve a more robust and a more accurate Egomotion estimate. And so the way we do this is to use a hybrid approach, which combines classical and data-driven components in a way that promotes accuracy, reliability, and interpretability, like I discussed near the start of this presentation. So here's an overview of this hybrid approach. So on the left, we use our tightly coupled SFM system that we just developed to produce Egomotion measurements. And on the right, we include a classical motion model based on INS integration that uses IMU data. And we combine these two sources of information within a Kalman filter. So essentially, we're relying on a data-driven component as a source of aiding to the system, just like we did with our zero velocity measurements in our foot-mounted inertial navigation system. And we're relying on a classical backend that consists of a Kalman filter with this integration-based motion model. And in doing so, the goal is essentially to leverage the robustness and generalization capability of the learned SFM framework, while also leveraging the benefits that come with using this classical estimation framework. So let's briefly look at the system in full, starting with the learned SFM system that I discussed earlier on. So here we have the depth and the Egomotion network, which are jointly trained by minimizing this photometric reconstruction loss. And our proposed solution is to incorporate IMU measurements, like we discussed in the last slide, using a Kalman filter. And this filter consists of this integration-based motion model, which takes inertial data as input. And so to train this system, rather than passing the Egomotion measurements directly from the network into the photometric reconstruction loss, we can instead pass them into the measurement model of the filter. And then the EKF will fuse these two sources of information and produce a refined or a filtered state estimate. And from this refined estimate, we can extract the Egomotion from the estimate and then pass it back into the view synthesis module to evaluate the reconstruction loss. And notably, since all of the Kalman filter components are differentiable, we can backpropagate from the loss through the filter and into the Egomotion network to train this system end-to-end. So we train the system end-to-end by minimizing the reconstruction loss for training samples consisting of a window of 10 images. And one interesting thing to note here is that by using this filter structure, we're actually able to sequentially link our predictions through time. So this means that this system is actually a form of recurrent neural network. And so this allows our current prediction to have an impact on these future loss terms. And then from these losses, we're actually able to backpropagate in the opposite direction to update the network weights at each time step. And this temporal connection is essentially a useful tool for regularizing the system. So next, we're just going to show one experiment that we conducted to evaluate the system. And like I've mentioned a few times, the main purpose of my research is to develop data-driven models that produce a more robust Egomotion estimate. And we want to do this in more degraded operating conditions. So this final experiment essentially tests the robustness of the system on this degraded environment that we collected. So we essentially applied two different modifications to the images within the Europe dataset. And so the first, in the first experiment that we did, we applied brightness, blurring, and shot noise transformations to a number of images in the test sequences. And in our second experiment, we applied frame skipping to simulate increased camera motion. And again, we didn't include these perturbations in the training set, so we just included them in the test set. So in both cases, we have evaluated the reliability of our system alongside a number of other classical VIO estimators. So we'll quickly summarize these results by reporting the number of failure cases for each estimator throughout the 20 degraded sequences that we generated. And we can see that within these sequences, the 3 classical systems shown on the right all failed a number of times, while our learned system was able to maintain tracking throughout this experiment. And typically, these feature-based systems failed as a result of either lost feature tracking or because the backend diverged as a result of having not enough good feature correspondences. So if we look at the translation error, we can see that in general, we're able to operate with less than 1 meter of error on these sequences. And if we compare it to a baseline system, which is a vision-only system, we can see that by adding the filter and the IMU measurements, we're able to substantially improve our accuracy. And lastly, just want to really quickly cover 2 final sort of aspects of this system. So first, because we're able to use a filter to properly incorporate inertial measurements into our state estimate, we're able to incorporate a scale parameter into our state estimate, which we actually use for scale recovery. So this plot just illustrates how the translation measurements produced from our network, they're nicely aligned with the ground truth translation, which shows that our learned measurement model is actually metrically scaled. And second, because we incorporate the filter structure, we're actually able to learn an uncertainty model that's associated with each measurement. So by providing the filter with this measurement uncertainty, we're actually able to properly fuse the data from the visual measurements and the inertial measurements. And so here we can just see that in areas where the error increases, we're able to inflate the covariance or the uncertainty. And what this means is that in these cases, the filter is essentially relying more on the IMU measurements than it is on the visual measurements to produce its estimate. And so this work, we recently published it at the Advanced Intelligent Mechatronics Conference this year, and thanks to Emmett for his help with this paper. So this essentially concludes the research that I've done here at UTIUS during my time as a PhD student. To really quickly recap, my approach has been to employ data-driven models for robust inertial and visual egomotion estimation. And I investigated these 3 applications, which includes inertial navigation for human localization, and then visual odometry and visual inertial odometry for robot localization. And just to briefly talk about some future work that can be done in this area, one thing I'm interested in is investigating how we can continue to leverage the vast amount of domain knowledge that we do have available to us in robotics when we're designing these data-driven components. So given all the domain knowledge that we have, the classical way to utilize this amount of domain knowledge is essentially to bake the domain knowledge directly into the handcrafted components that are contained within classical estimators. And like we've discussed, this can be problematic because these systems can be brittle and prone to failure. And in my work, I've shown sort of an alternative way to incorporate domain knowledge. And that's through self-supervised learning, which we use to train a robust data-driven models that are used for localization. So rather than baking this domain knowledge directly into our systems, we're able to use it to inform and to train our systems. And I've talked about a couple of ways that we've used domain knowledge. So for example, through structure from motion to formulate the self-supervised reconstruction loss, through also computer vision to incorporate our scale recovery loss. And lastly, I've incorporated domain knowledge from state estimation by using this differentiable filter for my visual inertial system. And so I think these are sort of good examples of how we're able to incorporate domain knowledge. And moving forward, I think that sort of this is an area that can be pursued further. And yeah, essentially we want to use this domain knowledge to inform our data-driven solutions and to enable self-supervised learning in different capacities. So thanks everyone for listening. I'd like to take a minute just to thank everyone, both from the past and the present from the STARS Lab. It's been such a great time the last 6 years spending time in the lab with everyone, and really grateful for all the great times we've had along the way. And thanks a lot to Jonathan for being a great supervisor. And thanks to Professor Scholig and Professor Deleterio for being on my doctoral committee. And lastly, just a big thank you goes out to all my family and friends who've been super supportive along the way. So with that, I'll conclude my talk.
We can take some questions. If anyone has a couple questions from the audience here, and then we'll open it up maybe to any questions locally.
Sure, yeah. Yeah, that's a really good question. So for the online folks, Mia was asking if by applying the zero velocity measurements in the foot mounted system, if we're able to account for some of the biases that exist in the sensor, so in the IMU. And the short answer is yes, you can definitely do that. But there's actually an interesting paper that came out that showed that really it doesn't actually impact the system very much, because the bias, the error you get from the biases is actually quite a bit lower than the overall error you get just by introducing systematic error from the zero velocity measurements themselves. And the reason for this is because when the foot lands on the ground, although it's approximately stationary, the IMU never actually is like perfectly stationary. So you're introducing a bit of systematic error into the system through that. So for that reason, that's sort of a larger source of error than what the other bias terms would provide. Yep.
For the foot mounted experiments again, do you think that your system could generalize to less structured environments? I think that there's collected as a flat surface, you might have used the same foot, or maybe you use a different something to equal that. Let's say you're walking in the wild, or you don't walk with the same pace, like let's say you walk quickly or slowly, or there's an obstacle in front of you, you have to like go over it.
Yeah.
Do you think your system could generalize to that? Or do you...
It's a good question. So again, with the foot mounted system, the question was, will the data-driven models actually be able to generalize to motion like outdoors, like maybe on different terrains? And I think that similar to the last question, it would be able to generalize if we're able to provide it with like the correct amount of training data. But the same problem will exist where maybe if you're landing on ground that isn't perfectly stable, you're going to introduce this systematic error because the IMU never actually is perfectly stationary. So it might make that problem worse, and the accuracy might reduce a little bit. But one way to deal with that could be some interesting opportunity for future work is to incorporate sort of uncertainty learning into the measurement model. So like I did with my final system, I learned an uncertainty model, and potentially based on how the foot falls, you're able to sort of inflate the uncertainty for the detections where your foot might not be perfectly stable. So that might be one way to like mitigate that challenge. Yeah, so the degradation experiment, just to visualize these again. Yeah, we did not include this in the training data at all. So these degradations, yeah, were just applied at test time. And yep, so that was kind of a cool result that we had was this demonstrated robustness and like generalization capability of our system. And I think one of the reasons why it generalized so well is because we are incorporating that filter structure. So you have sort of that that component that with the inertial data that you're incorporating isn't really affected by the perturbations. So that allows it to sort of generalize a bit better.
First of all, I just want to commend you. It was terrific. You did a great job explaining the very complex issue. The question I had, I want to play a little bit of devil's advocate. Explain that, well, you don't have GPS. That's what robotics like to think robocentric, probably not. Why put all of the effort in figuring out how to do things on the robot, and not so much on the infrastructure?
Mm-hmm.
I mean, this is a bigger question how one would approach involved, outside, even in campus, yes, or something like that. Indoors, maybe some Python system, all of that. Why not that? Why focus on robocentric?
Yeah, so for the question for the people online is essentially like why focus so much on robocentric sensing and localization rather than rely more on, I guess, external infrastructure, like better indoor localization systems, maybe improved GPS localization. It's a good question, and I would say that is all probably very important to develop as well alongside this. It might just be one of the reasons I think is like for people developing robots, it's a lot easier to just work on a self-contained system rather than setting up all the infrastructure needed to operate everywhere. So I guess the argument would be if you are able to achieve the desired accuracy level with a self-contained system, that is a better solution because it's very hard to have infrastructure like everywhere that you might want to operate. So I think in the long run, like maybe a self-contained system would just result in reduced cost overall rather than setting up all the infrastructure. But I do agree, like in the short term, especially with like things like self-driving vehicles, like it does make sense to start thinking about how to incorporate infrastructure that robots can use.
Okay, so we'll hop over to the Zoom. Hopefully this doesn't echo too much. A gentleman named Trevor on the Zoom has a question. A gentleman named Trevor. Trevor, feel free to turn on your mic.
Thank you, John. Hello from Montreal, Brandon. That was great. Very, very impressive set of work. It's almost like you did 2 theses, really, when you think about the foot mounted stuff and then all the car stuff too. So very, very impressive. My question is, I've got 2. One that's kind of general, and then one that's even more general than that. So you talked about why doing a like end-to-end learn VO is like more flexible than a handcrafted system, and that part of the reason for that is that you can continuously retrain. Did you do any experiments where you like trained on one data set and then trained the same model on another data set, and to see if like performance degrades at all? Or because I think the intuition is that at some point that's going to stop working, right? If you, in the infinite case of using all the data that you have. So yeah, I'm just curious your thoughts about that.
Yeah, it's a good question. Did everybody hear that fine? Okay. So yeah, the short answer is yes, we did actually do some tests on domain adaptation. So I'm just going to pull up the result if I can get it really quickly. But we essentially did just what you said. Training on one environment and then testing on another. And essentially, yeah, we showed that we were able to improve the accuracy just from doing that domain adaptation. So collecting a small amount of training data and in the new environment and then retraining. Yeah, I don't think I have like the actual data on me right now, but
That's okay.
yeah, we did do that. And it was sort of a preliminary experiment. So like we trained on the Oxford data set, which is another driving data set with sort of different camera parameters, very different like environment. And we essentially showed that by initially training on that data set and doing domain adaptation on the Kitty data set, we were able to like substantially improve the results.
Cool. Yeah, I mean, I think like your work was more focused on the assumption that like we're sticking with this paradigm and single data set. So it's almost more like it is like a future work type of question, but it's one that's bound to come up as you move on in this domain and in your new positions. And then, so my second question is, Val asked Karime this when she graduated, and I think it's a great one that doesn't get asked often enough. As a about to be, or I don't actually know when your defense is or was, but you'll be a doctor very soon, or potentially already are. What is your advice for aspiring doctors?
What is my advice?
It's a hard question to answer, potentially harder than the actual technical questions. So it could be just like one piece of advice, even if it's just something simple.
I would. John said, "I hope it's not. Don't do it."
Turn back now.
I would say like, hopefully this is useful, but like you want to start small, but like still try and aim big. So don't like get too focused on like really high level, like sort of long range research goals without sort of getting your feet wet. So work on like kind of incremental projects to start off first, get some experience publishing, and then sort of as you go, you'll be able to I guess focus more on sort of like your high level thesis goals. So yeah, try a lot of things, code things up, and try to get out of the publication early on, even if like it doesn't happen. I think just going through that process is a really useful thing to do early on. And say the one other thing is like really just find mentors in your lab or outside of your lab. If you get some people, like for example, Val helped me a lot when I first started, just kind of like getting my hands on stuff and writing my first paper. So if you have someone with like experience that can really help you out, that's like really, really valuable.
That's awesome. Thank you.
Thanks.
Any other ones on Zoom?
Okay, then I just wanted to say two things. Fantastic work, Randy. Congratulations, sir. Much. Also, I forgot to mention, I did not mention here. Brandon is also one of our server managers, which was fantastic, and also our benefits, our manager for the lab, which is also an incredibly important role. I neglected to mention that, and I think Brandon is
Mhm.
and yeah, when that happens, I guess I $400 back play / zero bills. So anyway, thank you for your service, sir. I very much appreciate it. All right. So with that, we'll thank Brandon one more time.
All right, thanks everyone.